Hello and welcome to the Specialist Maths July Headstart lecture. My name is Dash and I will be going through this lecture with you today. So this is the Headstart lecture run by ATAR Notes, and we are trying to give you the best head start that you can possibly have going into these next couple of topics so that when they come up in class, you're already a master of it. So Specialist 3 and 4, Unit 3, these topics you probably are through by now, so that's proofs by induction, vectors and matrices, vectors and complex numbers. Unit 4, well, we're talking integration, applications of integration, rates of change, differential equation, statistical inference, and this is what we are going into in depth today. So yeah, what we're going to talk about today. Topic 2 of Unit 4, which is modeling motion. If you've got a physics background, that'll really help here. Topic 3, statistical inference. So sample means, confidence intervals. And then right towards the end, we're going to have quite a few slides I've actually dedicated to it, talking about external exam advice, because if you have a rough plan already in your mind, when you get to the end of term 3, which is when you should really be starting to get into your study, you will have a rough plan already there and you are going to be doing almost to the full of your potential if you've already got a rough plan in your mind now. So this is recorded, which means that if you have a question about the content, about the questions, something working out, just put it in the live chat. I will answer any questions that you might have. Okay. Yeah, so that's the Q&A. If we're going to be going through, there's 90 slides today, so we're going to be going through at a good clip. That being said, all of these slides will be made available on the ATAR Notes website, so just go and search for them and you'll be able to get them. So don't be too worried if you don't get all of the information down straight away. Okay, so this is the yellow, completed green, what we're going into, as I mentioned before. So before we start with our content, I'll just say a brief introduction to who I am, as you would be unfamiliar with me. So I graduated last year with an ATAR 99.15. My name is Dash. I'm currently studying medicine at JCU, so I'm a first year student currently on holiday break. So I study at James Cook University, which is in Cairns, and that means that I get to live in this wonderful tropical environment, which is just absolutely beautiful. And part of enjoying, far north Queensland is running. I love running. I've done a marathon and an ultra marathon, and I'm also training for a marathon in July as well. So, in terms of how I did last year, obviously to get into medicine, it's quite competitive and you do want to really do well. I received 96 out of 100 for the year in specialist, and that included 50 out of 50 on the internals and 46 out of 50 on the externals. Obviously, you want as good of a buffer as you can get on those internals, but as you can see, it is very possible to do much better than you would have expected on your externals. I definitely didn't expect to do half so well on specialist or in terms of my ATAR as well. So having that self-belief is really important, and you can achieve your potential is so much higher than you can possibly imagine. But we're going to get into more of that right at the end. For now, let's knock off this content so that you will be masters at it. Okay, so ATAR Notes, there's lots of free resources. We provide this for free. I used and abused this as a student. I really recommend you do as well. I mean, you got study notes, lectures, there's a whole community, videos as well, newsletters, forums, etc. And the ATAR calc, I mean, if you haven't been through the ATAR calculator, it's a really valuable resource to see how you're tracking for the year. And then we have our paid resources, which are the high value resources. I definitely use some of them as a student. We got TuteSmart, so if you want tutoring from me, from elite graduates, send us an email, give us a phone call, and we will get you sorted. We've got study guides, and also one thing I will mention is ATAR Notes Plus. ATAR Notes Plus, this I used at the back half of last year for external exam study and for specialists. So for specialists, it was really valuable because they have these neat practice exams. There's like 3 practice exams for 3 years. Really good stuff because there's a marking guide as well. You can check off, oh, where would I got marks? Obviously, the marking guide for QCAA has part marks and has, you know, carry through errors, stuff like that. So looking at the marking guide will kind of, because usually you'd see, oh, I got it wrong. Oh no, I've lost all these marks. No, if you look at the marking guide, you're still getting part marks, and using and trying to get part marks is definitely an exam strategy that we'll talk about at the end. Yeah, and we've got an AI answer bot, which is super awesome. That was not available last year, or at least I did not use it. But I kind of wish I was a student this year to have a go at that. But yeah, 8 notes plus for all of your subjects, super valuable, super high value. Cannot recommend enough. There's topic tests in there as well, which was my first point of call for all of my subjects, just to see where my understanding is at. Then I cross-checked my understanding with the summary notes, the complete course notes, which are really comprehensive. And what I really like about them, they are written in terms of, first person. It's like I'm teaching you. Instead of being a stuffy textbook, we're talking about students teaching students in an understandable and comprehensible way. Okay, without further ado, let's get into content. So, topic 2, as I briefly introduced before, we're talking about modeling motion. So, the syllabus requires that you need to do all of these things for your exams. And obviously, these objectives are not very specific. They're just kind of like an overview of what you need to be doing textbook questions for. So, our first objective here is examine momentum, force, resultant force, action, and reaction. Once again, physics background would be fantastic, but I didn't do physics and still did very well. Consider constant and non-constant force, understand motion of a body under concurrent forces, consider and solve problems including involving motion in a straight line with both constant and non-constant acceleration, including simple harmonic motion, and use these expressions for acceleration. All of those are on the data booklet, so don't worry about them. I will note that throughout this lecture, several formulas are given, and often I won't highlight them or I'll give them a black box around them. But when I see something that I'm like, wow, that is not given in the data booklet, I will put a red box around it, and that means if you're going through this lecture, you should at least be writing those down because they are important. I would be, if you've got a data booklet handy, go grab it really quickly and go scribble down the red formulas. These are things that you have to memorize, and I'll tell you what's high value and what's not, because some things won't necessarily need to be memorized, but other things definitely will. But if you see red, it's worth writing down. Okay, so a little tip here. If you want to differentiate these different cog verbs here, search up QCAA Specialist Syllabus, and if you go to the contents page, you'll see a little definition section. Go to that page, and you'll be able to differentiate all of these different cog verbs, which is really valuable when you want to know, okay, how much depth do I actually need? But yeah, in general, you're going to have to know if something's popped up on here, you want to be doing a couple of questions for it pre-exams. So what we're going to consider first are these first 2 objectives, the examine and consider one for momentum, force, resultant force, and constant and non-constant force. Okay, so modeling motion, momentum. Now, momentum, it's in red, means you need to know this formula. P equals mv. P is momentum, so P we're referring to momentum. The m is referring to mass, and then v is velocity. So momentum equals mass times velocity, and we had to remember this formula. This was not given on the data booklet. Last question, last year's tech-free paper, it was a very hard question, and you had to use this formula as like the second last step. Now, our second thing that you need to appreciate is force is the rate of change of momentum in a system. So dp over dt. Now, the second one I 100% want you to memorize, you should be writing this down, is F equals ma. And what is this otherwise known as? I can hear you yelling through the screen. This is otherwise known as Newton's first law. And the units for this is kilogram meters per second squared, also known as newtons. So if you are writing the force of something, we always write just N for newtons. But yeah, you definitely need to know that force equals mass times acceleration. Okay, so force, acceleration, velocity, and displacement are all vector quantities. And vector quantities, what does that mean? They have direction. They are not just scalar, which is just a magnitude. They also have direction. So you should always give direction in your answer. If you're talking about force, acceleration, velocity, and displacement, are we talking about up, down, left, right, northeast, southwest, etc.? If it's giving you a direction, give that direction. If there's an angle that is denoting which way it is, I want you to give us that angle in the answer because you will be missing out on marks if you do not give those angles, those directions. Okay. These definitions aren't wrong, but they're not really practical when it comes to answering questions. So, you're going to have to remember those two red formulas, but the understanding this isn't physics, right? This is not, you're not going to get an explain question asking you to explain this. All you're going to have to do is memorize a couple of steps, and sometimes that's going to involve using F equals ma, P equals mv. So there's lots of forces acting on a particle, and we need to consider these when we answer questions. So the net force is just going to be the sum of all forces acting on an object. And you might be thinking, oh, well, what if a force is going the other way? Why would we be adding that? Well, if a force is going the other way, what is that force going to be? The force is going to be negative. So if we add them up, yes, we're going to take into account negative forces and get the net movement or the net force of that object, of that particle. So resultant force, it's in red, you need to memorize this, is F net equals the sum of all the forces. And you'll see the little arrow there. That means that it has direction. So that's a key thing to consider. But essentially what that formula is saying is you just have to add up all of the forces. If you add up all the forces, and I'm not talking about the magnitude of the forces, I mean the forces in terms of their I and J components. I and J, well, you're probably remembering that from complex numbers. The X, the horizontal, and the Y components, the vertical components, we add those up and we get the sum of where is it going horizontally, where is it going vertically. So to find acceleration, remembering that F equals ma, we first need to know the net force. And when you're answering questions, you need to appreciate that F is the net force. This is where we add up all the forces. Now we can work out the mass. Now we can work out the acceleration, etc. So acceleration with a little arrow because it's got direction equals F divided by m, and F is F net, as we've just learned. So there's a key here's a couple of definitions that kind of underline it, and this is key for your understanding because one of those objectives was understanding, right? So action. Action is the force of one particle on another. It's someone taking action, such as pushing a door open. It's something acting on another particle. However, reaction is the consequence of Newton's third law, which is that, every action has an equal and opposite reaction. And we see this, for example, with normal force or tension. So a second particle is going to exert an equal and opposite force on the first, i.e., the door exerts an equal and opposite force onto your hand. So there's two common reaction forces you might encounter in questions and do add a slight layer of complexity sometimes. So tension is any kind of force through string, chain, rope, etc. It's kind of like a pulling, keeping it stationary or sometimes not. And normal force is the force opposing gravity that an object exerts on another. Because if you've got, even as you're standing on the ground right now, sitting, whatever, you're not sinking through the ground, right? Which suggests that, your F net is zero. There is no acceleration despite you having mass. You are not moving, which means that even though there's force of gravity, which is F equals mg, which is pushing down through the ground, that is being opposed by the ground. And that is called the normal force. So the normal force is opposing gravity, directly. It directly opposes gravity, well, more like this, as you will soon see in some of these questions that we're going to go through today. So just because the forces acting on both objects are the same, doesn't mean the result on each object is the same. The acceleration of different objects is not going to be the same, despite equal forces. So an example that we're going to briefly go through, just in simple terms, is if we have a sumo wrestler who weighs 200 kilos running into a gymnast with a mass of 40 kilos, and the sumo wrestler is exerting a force of 800 newtons on the gymnast. When they collide, what is the force exerted by the gymnast on the sumo? So going the other way, or and the resulting acceleration experienced by both people. So for question A, you just need to apply Newton's third law here. So, but also put a little caveat, because it's opposite to the force applied, from sumo to gymnast, we're going to make it negative. So there's 800 newtons applied from sumo to gymnast. We're going to make it negative though, because it's opposing. It's an opposite reaction, right? It's a reaction. So the force of the gymnast on the sumo is going to be negative 800 newtons. Now for B, if we're finding acceleration, what are we thinking straight away? What formula has acceleration? It's going to be F equals ma. You do need to memorize this once again. So the acceleration of the gymnast, to find this, well, first we're going to have to plug in F net, or the force of the sumo on the gymnast, which is the mass of the gymnast times acceleration of the gymnast. We're trying to find acceleration of the gymnast here. We're going to have to do some rearranging. But we know that the force applied from sumo on gymnast is simply just 800 newtons. Then the mass of the gymnast is 40 kilos. Then we rearrange and we get that the acceleration of the gymnast is 20 meters per second squared. Now, for the acceleration of the sumo wrestler, a sumo, and you don't have to write it that like well written out. I would be using F of S on G or something like that, or F of S for just force of sumo. I would just be using S's and G's essentially. But you can, like I've written it out properly here. Okay, so now if we do the force of the gymnast on the sumo, well, what's going to happen is instead of the mass being 40 kilos for the mass of the gymnast, it's now going to be 200 kilos for the mass of the sumo. And the force is going to be negative 800 because we're talking about what's acting on the sumo, which was the reaction here. And so what we're going to find is that the acceleration of the sumo is negative 4 meters per second squared at collision. Okay, cool. So concurrent forces, when there's multiple forces acting on an object, it always helps to draw out a diagram of what's going on. No one is smart enough, or perhaps there's some super geniuses. I definitely do not classify in that, and I think that it is a mistake. You're going to be wasting more time trying to work it out in your head than if you were to just draw it out. And even if the diagram is not 100% right, or it's not to scale, or whatever, just give it a go with a diagram. You will thank me later. So when there's multiple forces acting on an object, draw out a diagram, please. Okay, so I'm going to show you an example of what a diagram would look like. Example, two people are pulling on a rock. Both people exert a force of 1,000 newtons. But person A is pulling to the right and person B is pulling upwards. So if I got like my mouse or something and I'm pulling up and pulling to the right, there's nothing opposing going up and there's nothing opposing going right. So it's both going to go right and up. So you'll see that this is kind of our vectors, right? This is what we were learning in year 11 and beginning of year 12 as well with our 3Ds, is we've got right and up, and there's nothing opposing them, so it's just going to be up here. And you'll see this on the diagram. So, and this is, of course, assuming a smooth surface, and in practicality, it would not be 100%, of course. So, the general rule of thumb is you want to resolve forces into horizontal and vertical planes, because we want to use our I and J components, and you can write it like that. You can also avoid it, but it's really just applying the same concept. We want horizontal and vertical planes, and even when we get to more complex examples, we still want that. So you want horizontal and vertical planes. Here it's easy because it's up and down. So yeah, I and J. Then we solve the net force, and that's going to then allow us to calculate acceleration or work out what the mass of the the mass of the object is if we're given a little bit more information. So this is how I would approach the question. First, draw a little rock. I cheated. I just got a photo from the internet. However, what you're going to want to do is arrange it into I and J. J being the horizontal, J being the vertical, I being the horizontal. So F of Y, so the vertical forces we've got to consider, F of Y is 1,000 newtons because person A is just pulling it up. Person B is just pulling it right. So what are we going to have? F of X equals 1,000 newtons. That's our horizontal. And what you should do is you should say, this would be a model answer for how to answer this question. You say resolving forces. Horizontal is this, vertical is this. The magnitude of those forces in total, because we know that the magnitude up is 1,000 newtons, magnitude right is 1,000 newtons, but in total, well, to calculate F net, we're going to have to add F of X to F of Y. And you could definitely show that as you could have a separate line. I've skipped the line, but you could say F of net equals F of X plus F of Y. Okay, if we're calculating magnitude of anything, consider it like any kind of vector quantity, even when we're calculating, our complex numbers. If we're calculating the magnitude, we want to square both of those two components and take the square root. If you're confused, just look at the formula sheet to remind you, and you'll see like x squared plus y squared, and that's essentially what's happening here. So we do that. We sub in 1,000 squared, and we get close to 1,414.21 newtons. Now we want to find the direction. And to find the direction, what we do is we go, and to remind yourself of this formula, I would go to the data booklet, go to the argz for the argument of complex numbers, but it's the same concept, right? What you want to do, and you could work this out with trig, but I wouldn't be too bothered with that because, trig or OA opposite would be down, we're not talking about hypotenuse, so the opposite of the angle here, adjacent, what's going to happen is we're going to have y over x. And if we sub it in here, we're always going to have the angle that we're interested in being tan theta equals, or tan -1 of y over x, the y over x component. So this is definitely something that you've got to familiarize yourself with. It's not in red, not strictly memorized, because like I said, you can go to the data booklet to cross-reference potentially. What I would recommend though is to definitely memorize that if you don't know is if we're talking about forces and you want to find that the direction, the magnitude is x squared plus y squared, square root of that. The direction is tan -1 of y over x. And here we sub in 1,000 over 1,000. That's just going to be 1. Tan -1, one of our exact values that, once again, you should have memorized, is 45 degrees. So if we were constructing a therefore statement here, we would say, therefore, the net force on the rock is 1,414 newton, 0.21 newtons at an angle of 45 degrees to the horizontal, because we're talking about the reference angle. It's always to the horizontal. Okay, consider the picture to the right, which hangs on a wall. Suppose that A and B are forces of tension, tension being reaction, of the two cables hanging the picture up. I ask you, what are we reacting to? We're reacting to gravity here. These forces are both 50 newtons, and the angle each cable makes with the horizontal is 30 degrees, sorry. How heavy is the sign? So, as with all of these questions, our first step is to arrange it into a diagram, and then we can, answer the question. So, because the horizontal, components, the tension forces, are going to cancel each other out, and that's because they're equal in magnitude, opposite in direction. That's the tension. Opposite and equal in its magnitude and direction. We're only going to be worried about our vertical components here to find the actual weight of the sign, and that's going to be in terms of gravity. And here I've arranged it so we've got a y-axis, an x-axis, a j, and an I. And then we've got our angles and our magnitudes in there as well. So if we are only considering what's in the vertical plane, the y plane, the j plane, what are we going to be left with? Okay, so the vertical component, because these two guys are going to be, you know, symmetrical essentially, TA of y and TB of y is going to be T sine theta. And we can just sub in the magnitude of the tension and, its direction. What we're left with is 50 sine 30, which we work out sine 30 is equal to half, and we're left with 25 newtons. Then, obviously, add them up because that was 1, obviously. Now, what we want to do is add essentially twice. So we get 25 plus 25 equals 50 newtons for F net here, or F net of the vertical, not in total yet. So we now need to apply a formula that I've now highlighted in red. This means that you need to memorize this formula, and that is working out what the force of gravity in terms of newtons is actually. So Fg equals mass of gravity, mass times gravity, mg. F equals mg, and if you come from a physics background, that's probably sounding pretty familiar. And if we're considering the force of gravity, well, it's always going to be vertical. So, okay, and we also have to consider that the system is equilibrium. And because it's an equilibrium, what does that mean? That means that F net is going to be 0, which means that these forces are going to be equal. That means that the force of gravity has to equal the force vertical in the tension, because where is this tension coming from? It's only a reactive force. We're not applying force here, which means it's just going to be equal to gravity. So if we rearrange the formula, divide Fg on both if we divide G on both sides to find the mass, what we're going to find is that the mass is approximately equal to 5.1 kilograms. Important to note, because newtons we're talking about kilogram meters per second squared, those are the units that we're essentially going to have here, kilograms. Or if it's acceleration, meters per second squared. Okay, this is going to be a harder example, and this is our plane, which can be annoying, and if you're from a physics background, you'll probably be pretty familiar with this already. So when there are multiple forces acting on an object, things can get really confusing. So in this question, I want you to assume that the mass of this particle is once again 200 kilograms. Now, I want you to find F in terms of our mean symbol, which we're going to call the coefficient of friction, so that the object can stay at rest on the ramp or move up as a constant velocity. You'll note here, this is a nice force diagram, because what we've done is we've already arranged that, gravity is going straight down. The normal force is going to be opposing the ramp. It's not actually going to be opposing gravity directly, because then gravity would be irrelevant. It's going to be opposing the ramp, and its vertical component is going to be opposing that of gravity. And you'll soon see how we can actually see these forces aren't balanced. This force diagram, as you can see, is not perfectly balanced, which means we're going to have movement. And the little reference angle we've got to work with here is 30 degrees. And we've got the force being applied, force of friction as well. Okay, so to solve the forces in this question, we're going to have to rotate our axes. Essentially what we want to do, once again, as I mentioned before, key step is we want to resolve into horizontal and vertical components. And sometimes those horizontal and vertical components, choosing the INJ directions, is not going to be, if you're looking down the page, it's not going to be just like that on the page. Sometimes you have to shift your point of view, almost rotate the page, because what you want to do is arrange your horizontal and vertical to be on the ramp, so that the ramp itself is, the horizontal, and the normal force is the vertical. That's going to be what we want to do. And the only force that's usually going to be left out, unless we have a harder example, is our force of gravity. So, like you would have done in year 10 physics, potentially, you're going to want to differentiate that force, separate that force into its horizontal and vertical components for the force of gravity, and work out what that little angle is in there, which is going to be 60 degrees. If we had our reference angle, be 30 over here. So therefore, resolving forces in the new horizontal and vertical I and J planes, we get perpendicular to the ramp that our normal force is going to be equal to the vertical component of gravity, and the vertical component of gravity is going to be mg for the, you know, for our magnitude of gravity times by cos 30, 30 being our direction, which equals 200 times 9.8 times 8.66 for our 30 degrees. You could also do that tech free, which is going to give us an answer of 1697.056 newtons. Then, parallel to the ramp, what we're going to get is our, we're going to be talking about gravity here. That's the force this is going to cause movement. There's no applied force currently. So, once again, the magnitude of gravity times its direction, so mg times sine 30 equals 200 times 9.8 times 0.5 equals 980. Another thing to memorize, gravity equals 9.8 meters per second squared. You do need to memorize that. Okay, so for the object to be at rest or moving at a constant velocity, that means that the acceleration is going to be zero, because acceleration is the derivative of velocity. And if velocity is constant, that means acceleration is zero. And that's according to Newton's first law as well. So our net force is zero. So overall, if we want to see if it's not moving, we're going to make the net force be zero, and this is called equilibrium. And we're going to solve, and we're going to find that force is therefore going to equal 980 plus 1697.056 times our coefficient of friction. And I've got this formula for the coefficient of friction up here in red. And I didn't memorize this pre-exams. If you're in physics, you probably already know it, but it isn't something that you get on your data booklet at the same time. Okay, so some tips for when you were working with concurrent forces, and I definitely recommend doing lots and lots of objective practice questions for these questions, because they are high yield and you will run into trouble if you haven't done a lot of questions for these. So always draw out the diagram. That's always step number one. Number one is always draw out the diagram, and you want to label all forces with directions and angles if it's given. Put in those magnitudes on the line. And next, what's going to happen? Well, if it's on a flat surface, we're not going to need to change the orientation. But step number two is always make a horizontal and vertical axes. We need to orient this so that we can use our trig, so that we can use our vectors to work out what is actually going on here. So if it's on a ramp, the usual ploy, the usual strategy is set out the I and J, the horizontal and the vertical, so that I is the same as the plane. So if the ramp is like this, we want to make this our horizontal, and then we make our normal force, which is equal and opposite, to our gravity's vertical, but it's like this, so that we've got 90 degrees. You then make that your J, your vertical axes. So this is just an example of a vector resolution question. We'd need to get more context to actually work out what that coefficient of friction here is. We just found an equation, and this isn't the most common question you can get, but I just wanted to show you that you can get a variety of questions, and it's really worth doing the complex examples, because conceptually they can be difficult, especially if you don't have a physics background. So worth going into, but you're going to get more different questions. Just remember those assumptions. If it's in equilibrium, there's going to be no movements. F net equals zero. But yeah, this does go over the fundamental principles. And if you at least do those first two steps, drawing a diagram, you know, say resolve, and then you write resolve into horizontal and vertical, you're going to be getting marks on these questions. Okay, so we're now going to move into those last three. So the syllabus requires that you can do all of these. The ones we're now going to talk about is consider and solve problems including motion in a straight line with both constant and non-constant acceleration, including simple harmonic motion. Fortunately, we have a formula for that. And we use these expressions for acceleration, which are also on the formula sheet on the data booklet. So don't be too stressed. Most of the formulas that you'll have to memorize, we did just brush over, so make sure you have written those ones down. So acceleration equals dv over dt. It's the derivative of the velocity, in other words, in terms of time. And it's also the second derivative of our position vector in terms of time. It's also equal to the velocity times the derivative of velocity in terms of x, which is our position, or equal to the derivative of half of velocity squared, in terms of our position. So if you're given in terms of x, so if you have a question, it's talking about velocity, it's referring to this last syllabus checkpoint here for modeling motion. And if it's in terms of x, what you want to do is you want to go d of half of the velocity squared in terms of x, because we're trying to. So if you're given an expression in terms of x, you want to use this expression here to find the acceleration, and then that's going to give you v squared in terms of x. Then you can square root it to just get v. So if you're given in terms of v, you either use a equals v times dv dx to get x as a function of v, or you can use acceleration equals dv over dt to get t as a function of v. So we would get t, and t is what you'll be most familiar with, but we can also have velocity in terms of the position vector, or in terms of position vector. Then we solve using differential expression. We're not going to go into them in too much detail. It's fairly simple as a concept. What you're going to want to do is just integrate both sides and set up a differential equation. We're not going to go into the chain rule today. I believe that is in the next lecture set. So if a particle is projected upwards with an initial velocity of u, the air resistance on the particle is 7 mv squared. Find the maximum height the particle reaches in terms of u. First, let's draw a diagram of what we know. This is just something I've found. So we're going to have the applied force, which pushes it up, but that's going to be opposed by air resistance plus gravity. And eventually, as the acceleration of the applied, the acceleration of the particle decreases, it's eventually going to go negative, and it's going to come down. And this is going to be applying similar concepts to projectile motion, which we did all the way back in Unit 3. But this is not as complicated as a question, but they're all applying similar concepts. A lot of the concepts are using similar principles, albeit with different equations and different expressions. So since we want the height reached, we want x in this expression. Now, these what I've got in black up top right here, these are kinematic equations, and you will probably be familiar with them from physics, but if you didn't do physics, these are expressions that we use. They're essentially using this is like a shortcut to the differential expressions. And because we will retouch on this in our next set of lectures, so make sure you stay tuned for those. I didn't want to go over differential expression in much detail. Perhaps you went over them in the lecture beforehand as well. But just to give a bit of a shorthand, I've given you these kinematic equations, which I don't recommend memorizing. If you know physics, you can use them. But we're essentially going to be using differential expressions to solve these, just different ways of approaching it. So this was our force question, right? The force being both negative because mass of gravity and the air resistance aren't pushing down. Force equals ma, so you got to sub in the force equals mass times acceleration. Now what you'll note is that mass is a common factor. So what we do, we divide that out. Now, because we're trying to find the max point is going to be when the velocity is going to be 0. Once it reaches that next point before it starts going down and the velocity becomes negative, and it's just finished being up, where it's positive, and that's going to be the height. So we're going to let x in this equation equal h for the height, and we're going to sub in that v equals 0. Then what we do is we rearrange to get in terms of h, and this is just, putting u on the other side, dividing out a negative, then dividing out that 2 times gravity plus 7u squared. And unfortunately, because we're not given extra information in this question, we're not actually going to be asked how to, get the, how to actually solve for the height, but we're going to have to get an expression for the height. So it's really important when you approach questions like this, because you can get a question where the final answer doesn't have exact numerical values. And that can be really frustrating. I know it definitely frustrates me when I can't get an exact value. So it's really important that you approach these in a very tactile manner and you just work out what you know. You apply differential expressions or kinematic equations and you work out an expression for it. And if you're not given the information, that's fine. It's okay to have an answer that's in terms of something else. And perhaps part D will give you an expression, but it's important to just go through the steps and sub in what you know, which is F equals MA, and just try and do some simplification where possible. So we've only really applied three bits of information, the kinematic equations. Alternatively, you could use differential expressions here. We've also applied that F equals MA, a thing to memorize. And we've applied that if it's at the max point and we're trying to find the height, velocity is going to equal 0. That's before it comes down, right? We've applied that, rearranged it, and we've solved for h. And h is in terms of this yucky expression in terms of u, but that's fine. Perhaps they give us the information, perhaps not. Okay, so simple harmonic motion, SHM. Simple harmonic motion, there was actually on the methods paper, a bit of side trivia, because I'm not sure if the methods papers are out yet. There was essentially a simple harmonic question on the methods paper, as I recall, and I tried solving it with methods and couldn't even think of it, so I just used specialist in the end. If you had a good understanding of specialist, it really paid dividends on that methods exam. The boys at my class that did specialist, we walked out and we looked around and we're like, oh wow, that was pretty good, pretty happy with that. And everyone else from methods was going, wow, that was incredibly difficult. What an awful paper. And we're looking around going, I don't know, that was a pretty good paper. You were in specialist. Massive advantage, especially on last year's paper. It was quite cruel. There was even a sim, there was even a specialist calculus by integration by substitution question, which was barely solvable using methods. And this was like question 16, so it's not even like the last question super hard, and it was complex unfamiliar for methods. So you've got a big advantage here, especially if they keep going that way where they've got more and more specialist questions. So keep that in mind. Be positive. This is going to benefit your methods. So, simple harmonic motion. We're talking about the movement of an object back and forth from a central point, like a pendulum, essentially. Yep, e.g. a pendulum. So, an object is said to be moving in simple harmonic motion if the acceleration, which is the derivative of x in terms of t, equals negative w squared, which is the angular velocity. Angular means how fast is it going around in terms of the angle, times the position vector, which is x. Therefore, the acceleration is always going to be proportional to the displacement, but opposite in its direction because it's always changing. So as a result, the further away that the object is from the center, the greater the tendency is for the object to return to the center. So the acceleration is decreasing because we're going really fast when we're kicking through past the center point. But as we go up and up, we can't keep going. At some point, we're going to reach a point of no return. The acceleration is going to go 0, then negative, and we're going to swing back the other way. And we're just going to continue like that in perpetuity. So from the previous slide, as I was saying, simple harmonic motion must have endpoints of motion, which we're going to call x equals a and x equals negative a. And you'll see this in the formula when we derive it. So the solutions to the differential expression that we had before are already solved, or are to be solved, are on your formula sheet. So you don't have to derive this formula every time. In fact, no time you're going to have to. Because it's related to the concept of differential expressions, which I'm hoping you've already gone over. If not, this is a comprehensive series and we are going to go over it in our next set of lectures. So you are going to go over it at some point. Don't be worried if you don't understand it now, because then we'll go over it then. I haven't seen the lectures for the last one, so perhaps you've already gone over that. So we're going to start by writing our formula. Velocity in terms of x. When do we use this? When we want to find something in terms of our position vector, as I said as a rule on the previous slide. And so we're going to write that the derivative of half the velocity squared divided by dx equals negative w squared angular velocity. times by x. So given the force equation for simple harmonic motion, we're just going to call k as a force constant, x being the displacement. We get F equals negative kx. Applying Newton's second law, we sub in ma equals mass times the second derivative of the displacement. We set up our differential equation, rewrite this expression so that we can apply our velocity formula. And what do we see? That w squared would be equal to k divided by the mass, which turns out to be our angular velocity. Now we rewrite it in terms of x and v, integrate both sides, which is the key concept in differential expressions. Because we're just talking about x here, we can just put w, negative w squared in front of this. We don't need to integrate that. And what we're left with is this expression here. Now we apply the fact that at maximum displacement, the velocity is going to be zero. So when it's all the way up here, well, the acceleration's already turned negative, but the velocity is going to be zero. So the constant is going to be equal to this. Then, we start rearranging and we see this formula here, which is on your data booklet. This one here. So I'm just hovering my mouse around. This is on your data booklet. And then we can do some rearranging and a second set of integration. So applying that velocity is dx dt, square rooting that squared there because it was v squared. Now, and then we can get rid of the w squared straight away. Now we separate variables, the x's and the t's, integrate both sides, and we get sine negative 1 x over a equals wt plus this constant. Then we rearrange it to be in terms of x, and we get the position vector, the position equation in terms of t for simple harmonic motion is going to be equal to x equals a being the maximum displacement in terms of x, of sine of w, which is the angular velocity, times by t plus a constant, which is almost like the time dilation. So if it's not at the center at 0, that's going to be a problem. And you are going to have to sub in that value if it was like plus 10 seconds or whatever it is for when it gets to that center. Perhaps it's minus. So we now have this equation that is on the data booklet where A is the amplitude, W is related to the period, it's our angular velocity, and the period is going to be equal to t, so how long that period is, divided by 2 pi over w. This is a formula you have to memorize. I've forgotten to put it in red. However, you do need to memorize this formula. So t equals 2 pi divided by w, our angular velocity. Alpha was our phase shift, as I said before. That's our constant. And the frequency equals f over 1 over t. So you need to know both of those so that you can answer these questions. So memorize both of those. And the frequency is how many cycles we get per second. So you can just work that out by going F equals 1 over T. You're going to have to memorize both those. T was the period, like in methods, and similar concept to methods, we've got 2 pi over B, but this time it's a W. So that's our angular velocity. This helps us to work out W. If we're given the period, we can then use it to find the angular velocity using this formula that you do have to memorize. T equals 2 pi divided by W. So when you're applying for questions in some simple harmonic motion, you're going to have to consider a couple of things, and these are the common things you're going to have to consider. Firstly, at the endpoints, when x equals a or x equals negative a, because they're both endpoints, two endpoints, the velocity is going to be 0 and the acceleration is going to be negative. And acceleration is in the opposite direction to displacement. We can see that from it's proportional, but it's negative. So at the center of motion, also x equals 0 and acceleration equals 0. So it's been doing all its speeding up on this little part here. So pendulum goes up, goes up. As it's coming down, it's doing all this acceleration. The acceleration is pretty big, but by the time it hits 0, gravity is no longer in its favor. And what we see happen is acceleration is now equal to 0. And then goes negative as we swing up. That negative eventually makes the velocity go to 0, and then negative as it swings back down this way, and then we'd have a high negative velocity here. So the maximum speed and hence both maximum and minimum velocity occur at the center of motion. So speed is going to be at its max when x equals 0. Acceleration is going to be 0 at x equals 0. Velocity is going to be 0 at these two endpoints, x equals a or x equals negative a. So if the center of motion of the object is not x equals 0, we use the following equations, and they're definitely more annoying. If you can make whatever is the center of motion be x equals 0, because otherwise it definitely does get frustrating. And you can also use cos to balance that out. So our acceleration, or d squared x divided by dt squared, equals negative w squared, our angular velocity, times by x, which if it's not our center, it's not x equals 0, what you do is you just minus that value from 0 away. So negative w squared times by x minus x0, what that value is. Now, we can also apply that to our other expressions. So whenever you see an x squared, or an x, sorry, what you'll essentially do is you'll put in x minus x0. And it's just a constant, but it's important to remember that it's a minus by that constant. And you should know this fairly well. And sometimes if you've gone through several questions, you'll just apply it in your head. Like it'll be, oh, it's not center of motion, therefore I'm just going to add here and minus it here, and that'll make sense. So yeah. Remember that if it's not the center of motion, what do you have to do? You have to minus it away in these expressions where the x is in brackets, it's multiplied by. But if we're actually talking in terms of the x, well, what are we going to do? We're just going to add it. And if this is the expression for the position, you can quite easily see that if we were to minus, you'll see the derivation of the minus, because to get it in terms of this, where we just sub it in, you would have to go x minus that addition to get to the actual center. Okay, so for knowing which equation to use, whether that's sine or cos, because both do work, you want to try and make the initial phase shift 0. So you use, if it's at a positive extreme of its motion, what we can do to skip having to have that little plus d or plus x0 is we can use x equals a cos wt. A cos, if that's it, it's a cos negative if it's at the negative extreme. And that's a little trick just to remember to make sure you're not doing all this excess working out, which is going to work out to be the same. So obviously, if it's an awkward one and it's not at starting at one of the extremes, so if it's giving you that this t equals 0, it's at one of the extremes or at the center, we're going to be able to use cos or sine. Sine is if it's at the actual center, cos is if it's at the two extremes. And that's so we don't have that phase shift, because that just adds a slight layer of complexity, which you don't want to have when you're ultimately answering questions. And if it's at the negative, we're going to use negative a sine wt. And then if it starts anywhere else, unfortunately, we're going to have to use our that little phase shift, so the little alpha or the little symbol there, which is another constant. And then we're going to have to substitute in boundary conditions to find the magnitude of A and what that phase shift will actually be. So you will be given boundary positions in these situations, of course. So sometimes it can be a bit frustrating when we have these phase shifts that's not starting at the center, and also when the center is not x equals 0, which is when we have our little plus d on the end, and also we have x minus that d value, or x minus the x0 value from those equations on the other page. Definitely write those equations down. They are definitely high value to at least have a bit of an understanding of them. Okay, so an example of this is if a particle is oscillating, if it's oscillating, what are we thinking? Like a pendulum. What does that mean? We're probably thinking simple harmonic motion. Also, we've just been talking about it, so it would make it likely. So its speed at the origin is 24 centimeters per second. Find velocity squared is A. B, what are the amplitude and the period? C, find the speed and the acceleration when x equals 2. So here's the sample answer. We're essentially just going to go to the data booklet and apply our expressions. And what have we been given? Well, we've been given acceleration already, but we also know that acceleration is equal for simple harmonic motion to negative w squared times x. And you don't need to know the derivation for all this because I've just gone through it before and it's not something you need to memorize. It would like have a skim through it because it is potentially a complex and fluid question, which I don't believe has been asked in the past, and obviously with differential expressions, it is something that you technically should be able to work out. And if you're familiar with that, well, chances are if you get that question on an exam, you're going to be able to construct a nice little proof and get access to all of those marks available. So now we need to apply, so we've worked out that our acceleration equals negative 16x and also equals negative w squared times x. Now we can factor out both that x and that x because they're on both sides, giving us that w squared equals 16, and that means that the angular velocity is going to be 4 radians per second. We just square root both sides. Now we substitute in that the speed at the origin, x equals 0, is 24 centimeters per second. We now use the second data booklet formula. Because we know what w is, we know that velocity is 0, and we know that x equals 0, now we can find a. Sub in x equals 0, what we're left with is 24 equals 4a, and that gives us that a equals 6 centimeters. Now we can find v squared, which equals 576 centimeters squared per second squared, and there's the working out. Now we can apply to find the amplitude in the period. The period, remember, equals 2 pi over w. We already know the amplitude is 6 from the prior question, so we're now working on b. And we just sub in 4 to 2 pi divided by w, which gives us that the period is pi over 2 seconds. So given that w equals 4 radians per second, a equals 6, we can now answer c, which is asking us find the speed and acceleration when x equals 2. Now, we're going to have to use two formulas because acceleration was negative w squared times x. Velocity equals this formula over here. When we've already square rooted it, you can use the formula in the data booklet too. Perfectly acceptable that you would do that. So we know that a equals 6, we sub in 4, and what we get is that velocity equals 16 times square root 2 centimeters per second, and that's just some simplification there. Now we sub in the acceleration at x equals 2, so remembering that because we're given that we want to find when x equals 2, we're not subbing in x equals 0 as we did before to find the initial conditions, or to find these constants that make up this expression. So what we're going to do is we're going to sub in x equals 2. We already know that w equals 4, negative 4 squared, and what we get is that acceleration equals negative 32 centimeters per second squared. How do we know it was centimeters per second squared? Well, we can go back to the question, and the units are centimeters per second. So what is the acceleration going to be? Well, it's going to be centimeters per second squared. Cool. Remembering that if you have any questions about the working out, about derivation of formulas, for example, about potential resources that are available to you, course unit structure, type them in the chat and I will answer them. Right, modeling motion. So this is a summary of what we've gone over in modeling motion. Net force equals the sum of all forces acting on an object. Always draw out a force diagram. This is key. Always draw out a force diagram. Resolve into horizontal and vertical components, rotating axes if you need to. You don't need to physically rotate them. Just label an X and a Y. Y for the normal, like draw a line through the normal, call that Y. Line across the ramp, call that X. But drawing that diagram, resolving into horizontal and vertical, and writing resolving into horizontal and vertical, there's marks assigned for this. This isn't, background that you have to do and you gain so much by skipping these steps and doing it in your head. Write out these questions, this properly. I did quite well because I wrote out all of these steps, and these steps are universal. Even if you're not super confident on this is your weakest topic. If you draw out a force diagram roughly, and then say resolve horizontally equals this, vertically equals this, you are going to be getting marks, and it is a necessary step to access the next couple of steps, whatever that different modification is that the question has had. And the classic example is an object on a ramp, and the forces you need to consider: force of gravity, force normal, etc., etc. So if you're asked to find accelerations, this is non-simple harmonic motion, you're gonna have to use. So if we've got acceleration is in terms of x, you use that formula to get v squared in terms of x, then we can square root it. If acceleration is given in terms of v, use v dx or dv dt to get x divided by t in x over t in terms of v. So those ones you're going to have to memorize, and they're the application of differential expressions as well. Now, finally, what we went over was simple harmonic motion, which was that b squared equals w squared a squared minus x squared. That's in your formula sheet. You don't need to memorize this. The key things to memorize, or just go over with some questions, is just when we're applying simple harmonic motion formulas, how do we find A? How do we find the phase shift? Having an understanding in terms of that, as I described on the previous slides, is definitely key. Okay, so we're now going to move on to our statistical inference, which is a slightly harder application of our methods syllabus. So the syllabus requires you to examine the concept of a sample mean x bar, capital X bar, is a random variable whose value varies between the samples where x is a random variable with mean of u and the standard deviation. Simulate repeated random sampling from a variety of distributions and a range of sample sizes to illustrate properties of the distribution of x across samples of fixed size n, including its mean, standard deviation. We have to use that formula, that's a memorized formula, to find the standard deviation because it's different to the standard deviation of x, where un, the standard deviation, are the mean of and standard deviation of x, and its approximate normality if n is large. Simulate repeated random sampling from a variety of distributions and a range of sample sizes to illustrate the approximate standard normality of x bar minus u divided by s divided by square root n for large samples where n is greater than square root 30. It's going to be normal, so that we'll talk about this in a second. I won't spoil it. We will go over this. Where s is the sample standard deviation, and then the standard deviation in that second objective is when we use that formula up there. What we're going to go through first is this first formula, this first objective, sorry, where we're examining the concept of the sample mean as a random variable, which is kind of talking, it's like the mean of the means, interestingly. So in methods, we go look at point estimates, which is of a single sample. What if we were to do lots and lots of samples and then examine what the, average mean is going to be? What's the standard deviation of that mean in each sample? And that's when we get this X bar, is it's talking about the mean of the mean, or different values of the mean, point estimates of the average point estimate, which is pretty cool. It's kind of like a more meta level of methods, and this is extremely high yield. More on confidence intervals when we get to it. Okay, so a sample is a small part of a whole, a subset of the entire population. An example of that would be flights of 100 people in a population. So samples are inferences about a population. Samples would be x1, x2, x3, all the way up to xn. N would be the sample size. So how many samples of those samples do we have? And these samples are independent of each other. If we're doing more samples, it's not going to influence what values we get. This is an assumption that we have to have. So x1 has no effect on x2. And similarly, for any two samples, if we're comparing them, there is no effect. So samples are identically distributed, i.e. if there's an underlying distribution behind each sample, normal, binomial, then these distributions are going to be the same. If the original sample was normal, the values that we then distribute here are also going to be normal, and same goes for binomial that we normally consider normal. The rule being it's got to be greater than 30, greater or equal to 30. So from methods, we'll consider this binomial distribution. So if we had, and we're looking at the number of sixes rolled in 20 rolls, 20 rolls, 20 trials. The probability of getting 6 is going to be 1 over 6, right? Assuming a fair-sided die. If we want to do this 500 times, well, one method would be that we use binomial distribution that you learn in methods. Alternatively, we can set each set of 20 rolls, as an individual experiment. Then we run the experiment 500 times, and now we're kind of looking more meta, is like n is now 500 instead of like 10,000 or whatever. We're now considering each thing as its own data point, and the point estimate being the number of, the number of sixes that we received in each thing. Then, if we go over 500 experiments, we're going more meta again. So, by running this experiment, we get samples of x1, x2, all the way up to x500. By the second assumption, each of these samples follow a binomial distribution with n equals 20 and p equals 1 over 6. So the sample mean is simply the average of the values of each sample. Similarly, it can be thought of as the average of all of the random variables. Therefore, the sample mean, capital X bar, can be given by adding up all of those little point estimates, or x's, all of those different samples, or the number of sixes that we got, and dividing that by n. And you might have to do that in a question. So some other important things to note about X are its mean and standard deviation. And what you will find is that the mean of X bar, is going to be the same. The mean is going to be, the same. And we're going to see that in a second. We're just introducing the different symbols that we use. So we use the mean symbol and also the standard deviation symbol. I'm not sure what that's called. So we'll see what happens to these variables when we then distribute it across our sample means. So here's a quick simulation. We'll go into some numbers. Suppose the population consists entirely of the numbers 0 and 1. Half the population is 0, half is 1. That means that the population mean is going to be 0.5. What happens if we take samples of increasing size from this population? And what we find is we have, if we have n1, we kind of have it even out. We got, different values of little x bar with different probabilities. And as we get wider and wider, it becomes smaller and smaller, almost continuous. And here you can see, as we increase n, the key thing, so what I want you to know from here, this simulation, is as we increase n, we approach a continuous shape. This would be normal here as we increase the shape. However, we're also so we're increasing the width of this curve. However, what we're doing is we're also making it almost more averaged out. The more number we have, the more accuracy our samples and therefore our sample means are going to have. So an easier way to visualize these results would be in graph form. I definitely work with graphs more than what we had before. So I prefer this, and you can see that the variance is decreasing as we go down, more approaching a continuous outlook. So in general, as n increases, the distribution should resemble the normal distribution, which is a bell curve. This is true no matter what the population distribution initially looks like, because as n becomes larger, we get a better approximation. So the properties of the sample mean, as I was just talking about before, is the mean is going to be the same. If the mean is 0.5, the mean of the sample mean is also going to be 0.5, and this is according to central limit theorem. But the standard deviation is going to be thinner. So we'll see that as n increases, the standard deviation of our sample means are going to be smaller. So it's going to be equal to S, or the standard deviation, divided by square root n, and you'll be confused. You're like, well, we got standard deviation twice here. We're talking about standard deviation of the population of each sample, and that'll be given to you as opposed to the standard deviation of the sample means. Here's just some modeling to show an illustration of central limit theorem. For me, what I want you to know is that as n increases, we get more normal distribution. So one of the rules is it normal? You've got to ask yourself, is it normal? N has to be equal or greater than 30 for it to be normal. Otherwise, we're just going to have too much variation, essentially. And of the sample means of, therefore, x bar, as you can see in these third ones, it's now normal. But if the original expression was normal, if the original population is distributed normally, we're also going to have a normal sample mean because it's going to follow it when we extrapolate it across several samples. So another way this can be written is like this, but in reality, we almost never know what the standard deviation is going to be. So what we do is we use the sample standard deviation, which is S, because, we don't know it until we've worked it out, and we use the formula that we just talked about before, S divided by square root n, and the larger n is, that means that we're going to have, altogether, we're going to have a more accurate normal shape. And this is generally used for large sample sizes where n is greater or equal to 30. So that's the key rule here. And you should, I haven't put it in red, don't believe this is on the data booklet, so make sure you write this down because sometimes you can be using this formula to work out values. Sometimes you're given a mean or a standard deviation, you have to use certain points to find vice versa. Right, capital X versus X bar. I really want to get this clear in your mind. So capital X is a single element chosen at random from the population. The distribution of X, if we were to graph it as a random variable, is the distribution of the whole population, and its parameters are mean equals u and the standard deviation. Whereas X bar is the mean of these measurements. So once again, looking more meta. Methods we learned this, here we're talking more meta. So X bar is the mean of these measurements of sample size n taken from the original population. The distribution of X bar is the sampling distribution, and it has parameters of mean equals u and standard deviation of S divided by square root n. So the mean of the population is also going to be the mean of the sample means. And one thing to note, that formula that you do have to memorize of S divided by square root n, you do have to memorize that, number one, and it's also referred to as the standard error of the mean. And we'll talk more about that when we get into our confidence intervals. Okay, time to apply this in a worked example. E.g., population has a mean of 50 and a standard deviation of 6. What are the mean and standard deviation of the sampling distribution for n equals 16? So we're now looking, if we were to take several samples, 16 samples, for example, what are we actually going to see happen? Well, what are we going to see happen between 16 and 20? And what we should see, standard deviation should decrease as we increase the sample size n. Here would be the answer. So for A, if we're just finding the mean, it's just going to be equal to the mean that we've been given for the population, which is 50. Whoops. And yeah, so we're just applying that. The standard deviation, we would sub in 6 divided by square root n being the 16 here, so 6 divided by 4, it would be 3 over 2. If you want, just type in the comments if you want me to write that out. I did forget to put it in. However, it's just applying the formula twice here. Then for B, the thing to note is while the mean is going to be the same, so still 50, the standard deviation is going to be 6 divided by square root n, which is going to be 20 for part B. So I've incorrectly labeled that as B. This is just part A and B. This is just part I and I2. of part A here. Part B, we would just sub in that, n is now 20, which means that we're going to have a slightly smaller standard deviation, and we're going to have ultimately the same mean. Mean stays the same. The mean of x bar is equal to the mean of the population, which is going to be 50. So here's a summary of sample means. It's altogether not a too difficult concept, but you just got to go over questions, get the process memorized in your head, and differentiating between x bar, because we've got several different mathematical terms here, which are, right now, you're probably going to be confused because, like, this is the first time you're learning it. And once you go over it in class, it will really be consolidated, and you will be confident with this and be acquiring these questions, which do make up easy marks on the exam. They are high yield, and they do appear year on year on year, as you will see when you go over the past papers in practice. So x is a random variable. Its mean, the population mean, is u, the standard deviation is s. The sample mean, x bar, is a random variable whose value is going to vary between the samples, like our point estimate. It's like the meta version of these different means. So the sampling distribution is going to be a representation of all possible sample means and how likely each value is for the sample means. Like, how likely is it we're going to get the sample mean? And the average sample mean is going to be equal to the mean of the population. So parameters of sampling distribution, the mean is still going to be equal to u, and standard deviation equals s divided by square root n, and you got to memorize that. And I will note that the key trend there is, as we increase n, the standard deviation is going to shrink. So yeah, as n gets larger, the sampling distribution resembles a normal distribution. And approximate normality for large sample sizes, where n is greater than 30, is x bar minus the mean divided by the standard deviation, which is s divided by square root n. If you have any questions, put them in the chat. And the two rules to determine if it's normal is n's got to be greater than 30, and if the original population proportion was normal, well, we'd expect that the sample proportion distribution is also going to be normal. Okay, confidence intervals, which is going to be the last thing we're going to be able to get into today. What are we going to be talking about? We're going to be talking about our interval estimates, confidence intervals, and interpretation of confidence intervals, which is kind of related to what we were talking about before, just more point estimates. So the last topic, it is interrelated with point estimates, as I said. However, we're more talking about population means. So if we have a population or a sample, the sample mean, we're looking meta at what the mean of that sample mean is going to be. Okay, so interval estimates. Interval estimates are a range of values for a statistic. For example, between 25 and 100 for the mean. Point estimates are exact values, so the mean equals 45. So an example would be if we wanted to estimate the amount of Year 12 students that have a laptop. We take a sample of 100 students, and we find that 60 of them own a laptop. Therefore, the point estimate would be 60, but that tends to be unreliable because it's just 1 point. So to be safe, what we do is we give an interval estimate instead. So between 55 and 65, we expect that the true population mean extrapolated over lots of samples would lie between 55 and 65. And that's the true point estimate, the true value, as you'll see in a second. So an interval estimate is going to have a certain confidence interval attached to it, i.e., how certain are we that the attained results are repeatable? And this is almost quite scientific in its nature, as you'll see in chem, physics, bio, etc. And we use confidence intervals a lot. I do men. We talk once again about confidence intervals and what it means if certain values lie within the confidence interval or out, and whether we can reject or accept the null hypothesis. So an example, if in a previous experiment, we might say that they are 95% confident that between 55 and 65% of Year 12 students own a laptop. And the lower bound of that range is a lower confidence limit. Higher bound equals the higher confidence limit. So the confidence interval for the sample mean utilizes the properties of the sampling distribution. A more accurate version of the confidence interval is this, and this is what is given in your formula booklet. You're just using x bar, the values you get for that, the estimate that is, minus z, z, as you've learned in methods. I'm not going to go over it again because we don't have time, but it's the values. There's only three, and I think I will put them up at the end. Then that times our standard deviation of the sample mean, i.e. S of the sample divided by square root n, and we have an upper or lower range. We basically take our point estimate, x bar, and we add z times the standard deviation. And this is on the formula sheet, so don't be too worried about this. And z is the quantile of the normal distribution we're considering, and there's three values that you do have to memorize. And here you go. So if you're using a graphics calculator, you can compute the relevant z value required to construct a confidence interval just using the standard deviation of z, as I'll talk about in methods, and the standard deviation being 1, the mean of z being 0. But it's always going to be between these 3 or 4 common values that you're going to be using. So at the 95th quantile, we're going to have z equals 1.65. 97.5th quantile, so for example, confidence interval 95, confidence interval 97.5, confidence interval 99%, 99.5% confidence interval. We're going to be using these values 1.645, 1.96, 2.33, 2.58. These are memorized values. You need to memorize these because otherwise you're not going to be able to answer questions and you will be losing marks and potentially not being able to access further marks down the road in these questions. Okay, so confidence interval. So how do we determine what quantile we need? It depends on the percentage confidence interval that we want. If we want a 1 minus x confidence interval, the z value, the quantile that we require, is the 1 minus x over 2 percentage quantile, i.e. the 95th quantile is used for a 90% confidence interval. Quantile does not equal confidence interval. I do want to make that quite clear. When you're reading it, it's quite easy to get confused, but here, what you want to know is 90% confidence interval is 1.645. 95% confidence interval is 1.96. 98% confidence interval is 2.33. 2.58 is 99 for the 99% confidence interval, and you need to know these Z values. So make sure you write this down. But yeah, just the quantile is different to the confidence interval. I think myself, I got confused just reading that just then. But yeah, this is what you need to memorize here. Okay, so this is an illustration of the Z graph, and I'm not going to spend too much time on it because we have a lot of content to go over. Graphically, this is what it means. Okay, so here's a work example. A group of 100 soccer players are practicing their free kicks. Each player takes 10 kicks each, and it is found that the average number of goals scored per player is 3.6. The number of goals scored is known to follow a normal distribution with standard deviation of 0.6. Find A, the 90% confidence interval, 95, 98, 99. And when we apply that formula, those formulas for the upper and lower limit, the only thing that's going to be changing is Z. Z is the only thing that's going to be changing from our 1.645 to, what was it? It was 1.96, 2.33, and 2.58. And this would be how you work it out. So here I've done plus or minus, but you could also just, just put it straight into the formula. I like to write out what we know. That is the sample mean, or x bar, is 3.6. Population standard deviation is 0.6 because we're just using that here. And the sample size is 100. We work it out and we get several different confidence intervals. And one thing that you'll realize with different confidence intervals is as we increase the level of confidence that we want to have, we are increasing the bandwidth. So the band of that interval is increasing. Initially it was like 3.5 to 3.7, but by the time we get to 99% confidence, we're at 3.45 to 3.75. We have a wider band because if we want to be more confident, that means we have to have a wider band for what the true value could be. But that means if we were to like run 100 simulations, that confidence interval is going to include that true value 99% of the time. And yeah, here's the simplified values for this question. So we can calculate the width of the interval by subtracting the endpoint values from each other, which gives us that the width equals 2 times z, s divided by square root n. You could also, if you don't want to memorize that, you can just derive it by subtracting the upper and lower endpoints from each other. And another term worth recognizing is that the margin of error equals z over square root over s divided by square root n. They're in red. Definitely memorize these ones. You could always derive them, but I would just memorize them for now. So if n increases and z and s are unchanged, this means that the width is going to decrease. So larger sample sizes means that we're going to have more accuracy in our confidence intervals due to less random error, right? Like science and maths, very interrelated, especially here. So confidence interval is narrow with a larger sample size. Larger quantile means we're going to have a larger z, which means a wider interval. Because quantile, remember, was very related to what level of confidence we had, but not quite. So quantile is not equal to the confidence interval. As I'm now trying to stress again and again, it is not equal. Just memorize those values. Not quantile is something you don't totally need to be super familiar with, but high yield, know those three values of z or those four values associated with the four levels of confidence. So you'll note that X bar is not included in these two formulas. And the reason for that is changes in mean only translate intervals. There's no effect on the actual size of, the interval. We're shifting it left and right if we have different means for our sample, our sample estimates. But we're not actually changing the width of that confidence interval. But if S, the standard deviation, increases, that means that our width is also going to increase because there's now more variability. So think logically. If we want to be confident we've got true value, if we're increasing the level of confidence we want, it's going to get larger. If we increase, or if the variability, the S is increased, it's also going to increase. If we've got a larger sample size, we can be more confident, so it's going to decrease. And if we change what that estimate is, X bar, it's not actually going to affect the width and the margin of error of this formula. And you'll see that the width is double margin of error true on those formulas. Okay, so now let's have a go at simulating some. Well, we're not going to have a go. Um, I'll refer to your website because we don't have time today. If you need an in-depth look at any of these concepts, I really do recommend tutoring. Tutoring is definitely very worthwhile. Okay, so we start with a quantile in advance, example being a 95% confidence interval, and that gives us a predetermined value of z. The value of 95% is represented by the z value that we have in the question. So we start with a sample size n, and we generate n observations and samples. We then calculate x bar and s and repeat it n times to obtain an n confidence intervals. A website to simulate that. You can click on that link, or it won't be working. If you want me to drop that link, just let me know in the chat and I'll get it for you. Okay, so now let's interpret confidence intervals. So if you were to do those simulations, you should find that some and most of those confidence intervals contain the true mean u or some won't. And we can't actually determine the true mean u because our experiments are always going to have some level of random error, some flaw, something like that. However, in the long run, if we model confidence intervals again and again and again, 95% of the time, if it's a 95% confidence interval, it's going to contain u. And this is a similar concept in methods. So, the 95% confidence means that 19 out of 20 times or 95 out of 100 times, it's going to contain the true value. So if we calculated n 95% confidence intervals, you can calculate how many of them will contain the true mean by just timesing 0.95 times n. And the numbers should be close to theoretical. Because statistics is a central tenet of science, and it is overall pretty, pretty accurate and pretty useful. So here is a brief summary. Interval estimates is the range of values for a statistics. For a statistic, confidence intervals are the interval estimates with a level of confidence attached. Confidence interval formula, this is in your data booklet, don't need to memorize. Do you need to memorize the margin of error and the width formula? Do you memorize them? And our three Z values for our quantiles. Quantiles, not so relevant, but you need to know that second slide, which was the three values and their corresponding Z. But yeah, if you wanted to work it out, 1 minus x confidence interval is the 1 minus x divided by 2% quantile. And that's where we get differences between our quantile and our confidence interval values. The most common, this is just one of the three that you should memorize. There are four, but I only memorized three, excluding the 98% one, was 95% confidence interval, Z equals 1.96, which we then use in the confidence interval formula. The interpretation of that means that if we've got a 95% confidence interval in the long run, 95% of confidence intervals are going to contain the true mean. And here are the two formulas that you need to memorize. Width of interval equals 2z times s divided by square root n. Margin of error equals z times s divided by square root n. S being the sample or population, standard deviation. Okay, cool. Before we just quickly move on, because we are now into external exam prep, so well done for getting through the content. And we've got a good half an hour. This should be pretty good. I will note that the last tech active last external exam question last year, don't know if it's up yet, but it was a confidence interval question. And there was something like 8 marks attributed to it. And part of my success on that external exam was that question, significant amount actually, because I got that question fully right. And other people did as well, even people who hadn't done so much study. And it was just like applying two different confidence intervals, finding their upper and lower bounds. And it was just applying data book formulas. It was probably one of the easiest last external exam questions, which is usually notoriously difficult, those last three. And it was pretty good. This is high yield. You can get very good marks on an external if you have good understanding of confidence intervals. It's high yield. Learn confidence intervals and have a good understanding. Watch a YouTube video if you have to. Okay, and this leads on nicely to what we're going to be talking about now, which is advice. We're talking about how you are going to ace these externals and achieve your full potential. So when you're prepping for your externals, I definitely recommend starting before the term 4 holidays. Definitely be doing stuff over the term 4 holidays though. I was a couple of weeks out from term 4 holidays when I really started getting into it. Other people need more, other people need less. So you want to go through every dot point in the syllabus and write the general process for that type of question and any strategies that you pick up. And we're going to go through a couple of them, or at least dot point them, and then we have some practice questions at the end. And if you've got the PowerPoint open, not sure when we're going to release that, but if you have got it open, definitely type in those questions, or any questions you might have about the derivation and the calculation of those questions. So make sure you get the basics. Those first couple of steps that are pretty universal that are going to help you to pass specialists because they want you to pass at the end of the day. And the way you pass is just by knowing those basic steps across all of them. Then you want to practice the hardest questions you can find because you want to develop problem solving skills for complex unfamiliar questions. And in general, I would describe the last three questions of any specialist paper as complex unfamiliar. They've always got a twist, a little bit of a concept difference, which makes them universally fairly difficult. This is going to develop your problem solving skills and help you to get the highest possible mark that you can on a specialist external exam. And it's almost like trickle down understanding. And what I mean by that is if you're applying a really hard concept, for example, in medicine, I learn applications of chemistry to drugs, biology to drugs and how they interact, or mechanisms of action of hormones or diseases, pathology, etc. It's almost like a trickle down understanding that is going to improve your skills in answering questions that are at the more basic level. You want to get the basics first, and this is really what today has been about, is helping you understand the basics. You want to do the simple, familiar 1 or 2 mark questions, practice lots of those. Once you're comfortable with that, jump straight to the hard ones. And like, it will be hard. It should be hard. This is a common misconception that leads a lot of people to give up, is if the going gets tough and it is a really rough question, ultimately that means you're learning. If it's not tough, you're not learning and it's no yield, it's zero yield. And a lot of people who study way too much and excessively aren't doing the harder things. They're just recapping what they already know. So for me, what I want you to do is do the hard questions, because you are it's high yield because you're inadvertently learning adjacent concepts which are related to that, especially when it's tying in 3 concepts. It's like you get more bang for your buck. You get learning 3 concepts for the price of one. And use as many resources you can find: textbooks, study guides, libraries, Googling questions. I think I did like 3 practice exams a day across all of my subjects, of course, in the 40 or 50 days I had revising. And I worked out, how many practice exams I had for each, including topic tests, etc., that you find on 8 Notes Plus. I got a significant amount of the resources I had available from 8 Notes Plus, but also my teacher was very kind, gave me some practice exams that I also went through, but a significant amount of the resources I went through were from 8 Notes Plus. So once again, cannot recommend it enough. I am speaking from personal experience. It's worthwhile. Okay, so this um, this is kind of like a little summary of how, and this is including Unit 3, of how to approach different questions for each objective. And writing out this and trying to understand it, like, okay, what is this related to? Trying to get in your head so it's not total gibberish means that you have a really good concept of, you're going to be able to answer a lot of questions and apply this. So I would definitely recommend, once you get up to, once this is released, go onto this PowerPoint and just copy this out, because this is a nice little summary. And then, we haven't got everything here. It's just a little bit of a taste. This is to give you a head start. Then you would go on to Unit 4 as well and other topics in Unit 3. But you want to go through all the objectives essentially and answer them, you know, write some notes. What do you need to know? And if you are, reach out if you do need help, um, in whatever form that may be, whether that's looking through resources, etc. But also, you can use resources like ChatGPT and AI tools. You want to stay with the curve, and that means if you don't understand something, you can now use AI resources to actually expand your understanding. You can copy and paste the objective in and say, okay, dot point all the things I need to know for this. Then, obviously, AI is just increased and increased and increased. I used it a bit in year 12, not for assignments, obviously, but for understanding. It's a language model and it's quite capable of helping you to understand, and it is pretty good at math. I would be using that to answer these objectives. Say, oh, just dot point what I need to know for my external exam, and it'll definitely help with that. If you aren't confident on your own notes or the PowerPoints that your teachers provided, or indeed this lecture, but yeah, I'd be summarizing them, and then you'll have these like a little summary book, and you can staple together like these little A4 papers, and it does help. Other things to do. This is just an example of other little tricks that you can apply, and I'm not going to go through them now because we only have 19 minutes left, and I still have a good 15 slides to go through. So, yeah, these are other little tricks you can use. I would write these down. They're good notes, and once again, the PowerPoint will be available. If you have any questions about any of the content in here, please ask me. I will definitely answer your question to the best of my ability. Internal exam prep. Obviously, It's now July. You've probably got one left, your IA3. And the IA3 is a good point. This is like perhaps if you weren't studying to the best of your ability in the start of the year, this is a good opportunity to start gaining momentum before your external exam. This is time to gain momentum. This is when you want to be picking up ahead of your IA3. You want to make sure you know those concepts pretty well. Do those revision questions because obviously when it's internal, it's your teacher that's giving you questions. You want to, it's going to indicate what's on the exam, right? They're going to show you what's on the exam with their revision questions. Sometimes they give you past papers. Sometimes other schools have like exact questions that are just transferable. They just change some numbers. And what it's going to do is cement the process in your brain. After that, obviously do as many questions and get your hands on, and you'll do really well. It's a no-brainer. And if you're willing to put the effort in, you will do super well. If you just do question, 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 etc. But if you're perhaps like, especially for internals, if you're like wondering what other questions you could get, and you don't want to go to textbook questions yet because sometimes they're relevant, sometimes they can be a bit applying formulas you don't need to know, etc. Brainstorm ways in which the questions that your teacher has given you can be changed to be harder. So, given different bits of information, for example, or you weren't given the formula, or it wasn't stepped out A, B, C, D. So, those are the questions that your teacher is going to make complex unfamiliar, especially if your teacher isn't especially nice in the way that they provide their revision questions. They won't give you the complex unfamiliar level. And so, to get there, you've got to rephrase questions. Or one little trick I do is go backwards. So um, this works with textbook questions as well. Make every question complex and familiar. Also works with methods. You cover up part A, B, C so that you have to go straight to D. Then you kind of link. So you're rebuilding neural pathways where you're linking all those parts to be the same question. And that's what a complex familiar or unfamiliar question will do. It won't give you the steps. It'll just say work this out, and it'll be this like wow 5-6 mark question. That's how you work it out. And then yeah, so using variables instead of numbers or prove that can be an interesting question. Depends how strong your proof concepts are as well, or incorporating two different topics. Complex unfamiliar questions will incorporate two or three topics often, especially what I call the whack complex unfamiliar questions. So, writing notes is oh so good. Like if you have summary notes for each topic before you do your external exam, definitely like line up the three sets of Headstart lectures. Watch it again potentially, or just tab through them and just like, yeah, yeah, know that, know that, know that, know that. Oh, dash that we didn't actually have to know this derivation, so I won't worry about that. Oh, but I see it's a differential expression. I now know how to do that. So this is an example question. Instead of answering it, go over different ways it could be arranged, different ways that we could work it out. For example, revolving it around the x-axis, volume, um, using integration. This is applications of integration in its finest, isn't it? Um, well, of course, that's the basic question, but instead we revolve it around the x-axis. What changes? Sometimes there's some really hard textbook questions, and in fact, I think one of the 800 NEAT papers was very difficult, which is good. And like the steps, you had to like use a matrix transformation, and technically that was unit one. If it's on the like there's formulas and stuff on the data booklet, if you didn't know how to do that, they can't give you that question. It's tough. It's a whack external exam question, which means like complex unfamiliar, yeah, it's hard, but it's at an internal level. Whack is questions where no one in the state will get it. And sometimes there's whack questions on external exams where it is crazy hard and no one in the state will get it. Those points are deducted off the total available. So yeah, work backwards. For example, you're given volume of B, then you find the radius. There's different ways you can work it out and just brainstorm because it's going to build your understanding. If you are thinking like this, making dot points like this, you're going to do extremely well on your external exam. You have my word that you'll do really well if you're looking at concepts similar to this and kind of thinking, how could this question be rearranged? How could we work this out? Okay, here is some general exam prep. So every single time you make a mistake, make note of it so that you remember not to make that same mistake on the day. And I actually did this too. Like this is direct from what I used to do is I'd go to the front of my book and I would just go dot point. What did I do wrong? What did I do wrong? What did I do wrong? And when I was going to, or another good way would be get an Excel document as you're going through practice exams, which there's a lot of. And for maths, just tabbing over these slides, you'll be like, you'll refresh the concepts. Then it'll be the practice question where you really learn it properly because maths is less content based, more application, right? So every time you make a mistake, make a note of it in the Excel doc. Say, oh, I lost here, and you'll see some common ones pick up. And perhaps you want to review textbook questions for that topic. So a lot of and then that helps prevent you making the same mistake on the day. So a lot of students have an amazing understanding of the concepts, but are deficient in algebra skills, which are especially important when we're doing tech for exams. Reading some books on the psychology of motivation and studying can help, but obviously, and that's to avoid procrastination and laziness. But ultimately, there's a modern society gets sucked into this void where we kind of, you know, are often it's the motivation. I feel motivated, but then you don't do the action, and then you just wait for the next motivation, the next Instagram reel or whatever it is that's going to motivate you. And it's like, at the end of the day, you just got to do the thing, and it's going to suck. But if you know, it's not good to procrastinate. There's no 24 hours of insane study for specialist maths that is going to save you, or even a week. You need several weeks extrapolate, and you need to be doing work now. You need to be doing the homework now if you really want to achieve your full potential. Specialist is hard, but if you do the work, you will see the results. Everything is doable. There is no question that doesn't have an answer. So, yeah, some tips that help me. If you feel yourself losing focus, just like sit back and just oxygenate your brain, just breathe. Do it. It's almost like a mini meditation. It's not pseudoscience, it's definitely real. Um, doing questions which are just too hard is the most productive way. You don't want to do something where like you haven't done the basics. That's why I say do the basics, then do the super hard questions. Because once you've done the basics, it's within your reach. If you've done the basics, every question is within your reach. It's just about linking the basics and a couple of little extra things. So do the too hard questions because that's the most productive way. Listening to the same songs over and over can actually help. You can't see the song I put in, but also classical music improves your IQ. But it's an acquired taste. We'll just say that. So during an exam, it's for higher achievers. It's not that you don't understand. It's actually the little small mistakes. And I'm definitely guilty for this. I make little mistakes, even transcription errors, and it's amazing to me that I got about like 92% on an external exam when I made lots of silly mistakes and on practice exams didn't do especially well, but I was attempting every question and going through the answers. I didn't just go, oh, I was wrong. You go through and you write out. So if you get a question wrong in practice, you at least write out the complex unfamiliar steps. So every time you do an answer, I know it's boring, but this is how you get really high scores. Check you've written down every formula right. Check that you've copied down values correctly so you don't get a transcription error. You haven't misread a number. In tech-free tests, you can always mentally check your arithmetic, figure out what mistakes you make the most often, and focus on these in the exam. When you've got from your Excel doc, have that written down, and then when you're doing a question where you're applying that concept, be conscious of that. Be like, okay, I made a mistake here. What am I going to look at? I'm going to check that I've done this right. Figure out some strategies that help. So practice questions until they make you so bored you rather die than do it again. This is burning the process into your brain. It's like your brain is a muscle. It's not technically a muscle, according to anatomy. However, it can also, you do make new neural connections. And if it sucks, if it's really hard, like a good workout, it is going to make you smarter. And you want to turn your negative self talk around from I'm so stressed I'm going to make so many mistakes too. I'm so prepared. I know that I'm going to be able to figure out what's going to be thrown at you. The best singular advice that I can give you is answer every single question. There was a absolutely wacky question to do with like integers and stuff that was on last year's paper, which was so obscure and it was only worth like 4 marks. But I just wrote random stuff, and part of what may have got me such a good grade was a lot of people just left that blank. I just wrote random stuff, rearranged it, did whatever in the hope that I'll get a mark because it may so happen that it was the first step. Conceptually, I didn't understand how you figured it out, and that's okay. You can still do well because it was almost off syllabus. It was ridiculous. But anyway, it's a wacky question. Sometimes you do get them. But I just rearranged it, wrote anything I could think of because you're not too time poor. Complex questions, make sure communication is on point, write all the formulas, define all the variables, write headings, work it out nicely. It helps your understanding too. And try and visualize where you're getting the marks for in that for that topic because you know there's gonna if you can do that, then you'll be able to like dot point or do headings, and it'll make it really easy for the marker and really easy for your understanding. You'll be getting the marks more often than not. Put units, please. Please put units. 1 mark questions generally only require an answer with units if it's necessary. I would just put units anyway. Though, like, it costs you nothing. Just put the units. It's not going to cost you anything. Okay. Final advice is to look after yourself. You're a human being, and the specialist external exam is the hardest external exam. Specialist is hard, but it's altogether doable. You can do it. It's not, you know, this. It's not university level. Well, some of it is. I've seen what the engineering students do, but ultimately, it's not some cutting edge theorem. It's fairly simple as the application in calculus. This is the base. This isn't the insane like quantum mechanics application. You can do it, is what I'm trying to say. So eat enough, sleep enough, make sure you're getting your 8, 9 hours, and drink enough water. If you don't have enough water, it actually makes you more irritable scientifically, because of osmotic gradients in your brain. You need to drink enough water. Just have a water bottle next to you whenever you study, or if it's iced coffee or whatever it is. Coffee definitely does help during exams, but don't have too much coffee. Otherwise, like my hands are always shaking. I definitely over caffeinate before exams, even my last set of exams. However, yeah, you don't want to have too much especially if you're prone to anxiety. I'm fairly calm as a person. I don't get too upset by things, but if you are over caffeinating, it can cause problems. So don't spend every day studying. Less is more, but it's about the quality. It's about doing those hard questions. There's a lot of pressure, but it's a learning curve. Life is a learning curve, and this is just yet another example. So there's lots of ways to get like if you find yourself, perhaps you're already several marks down, you're already failing. You will be able to pick that up. Trust me, you will be able to pass for the year. However, um, ATAR isn't the only way to get to where you need. There's always pathways, and it's a year of your life, university or TAFE or whatever it is going to be a really fun time in your life, and you're not going to hate it. It will. It's the journey, not the destination. Okay, we are now going to go into questions. We've only got 5 minutes, and I am bound by time, so we're only going to duck through them really quickly. But yeah, make sure if you need any help with your studies, reach out to our team via our website and we'll help you out. Also on the forums, ATAR Notes Plus can definitely help as well. But tutoring is available. I myself am a tutor, and tutoring has helped a lot of people to get through their year. Okay, so here are some questions. I'm going to be cut off by time. So what I'm going to do is, once again, you can definitely, like, here are just some solutions. I definitely recommend going over these questions and working out as best you can. Perhaps you save them for revision, whatever suits. But then you can refer to the answers and cross-check. As you can see, key concepts that we're applying. I'm going to use this as more of like a summary. We're using formula from the data sheet, the maximum. So if it's at the origin, what does that mean? Acceleration equals 0. Velocity is 0 at the two extremes. And what we're doing is a bit of rearranging here. 2 is more simple harmonic motion, applying the formula for period. And because this is a proof, we're just rearranging into this form, which is on the data booklet. Don't think too hard about proofs; they are doable. Okay, next we're using force equals mass acceleration. You need to know that. And we use a key relationship between force and velocity, which I believe is a kinematic equation, and initial conditions to solve for things. Then, unfortunately, I did leave in a question for differential expressions, which means we have to separate variables and then integrate. So not totally mutually exclusive topics here. And then in our final part, once again, we have to apply that when velocity equals 0, the particle is stopped. And then we did have to use, and then we integrate, etc., and rearrange. And then you would need a calculator to finish this off, otherwise you would leave it in LN504 form. Now this is what is this? Another, what question? 4. 4, we're talking again, simple harmonic motion. This one, there's a time dilation, or is there? No, there's not, because it's 0. There's 2 of them here, and we can calculate them in total, kind of just mixing and mashing some concepts here. The max velocity is going to occur when we are at 0, when acceleration is 0. So you can find that position where the origin is, whether it be sine or cos. Yeah. 5, it's just a simple sample mean and sample standard deviation question. We're just subbing in values here to the formulas that I said for you to memorize initially. Question 6, we're now using for confidence interval. Before you work out a confidence interval, we're going to work out the standard deviation. Or you can just sub it, the sample standard deviation, straight into the formula. That would also work. And we get a confidence interval of this. It's 1.96. What was 1.96? That was 95%. So once again, you have to memorize those values. Now we've got a rearranging question, so a bit more complex and familiar. We are rearranging using the error formulas. So memorizing them is really key. 7a, once again, it's another confidence interval. 7b, we're actually given confidence interval. Now what's n? What's n to find for that confidence interval? And this was a similar question that we had on last year's external exam. So really key concept, but really satisfying when you get a solution, to be honest. And yeah, so that was our last question, and here is confirmation of final answers. So overall, I would definitely have confidence going into the external exam. There's no point second guessing yourself when it comes to your answers. Once again, if you have any questions, chuck them in the live chat or reach out by our website. And those solutions are all there. So when the PowerPoint is uploaded for that lecture, 2024 July Specialist 3 and 4 lecture, you can go through them at your leisure and interpret those solutions. But they're just applying what we've learnt today, except for the differential expressions part. But yeah, that is going to conclude today's lecture. Well done for sticking by with me. You will do well in Specialist, and if you put in the work, you will see the returns. So please, please put in the work. All right, that concludes today. I hope you enjoyed it, and it has really given you a head start for Specialist 3 and 4 to give you that confidence that you need going into the external exam. You've got this.